example, if we go 1 standard deviation of x to the right, and then y will go on average only r times standard deviation of y. It doesn't go 1 times standard deviation of y, it will go only r times standard deviation. So if r is less than 1, then the amount that it will go up is less than the complete SD. So that is why it is like here. It can go like this. It has gone. So full standard deviation is from here to here. So this height is only, in this case, 0.4 times the standard deviation of y. So that's what explained here. If someone is 1 standard deviation taller than the average height, they are only 0.4 times standard deviation of weights heavier than the average. So it's not complete 1 standard deviation above the average of weight, only 0.4 times. So generally, therefore, we say if you increase your x value by 1 standard deviation, then the y will increase or decrease depending on whether you have positive or negative relationship by r times standard deviation of y. R times standard deviation of y. So in this case, if you look at an example, if you consider these people have average height 70, standard deviation is 3. So if you consider all the people whose heights are 73, that is 1 standard deviation above the height, their weights, if you consider, will be 0.4 times standard deviation of y, that is 0.4 times 45, above the average of weights. So that's what is explained here. Numerically, it will be this much above the average of weight. The average of weight is equal to 180. So that will be 180 plus this amount 18. So that 198 will be the average weight of people whose heights are 73 inches. So that's how we generally predict in this case. So here, without any formula or any mathematical equation between x and y. Right? So that is the difference between this book and most of the other books. All the other books, first of all, get the equation and then apply, plug in the value and get the value. But here it's explaining what is actually happening here. So the solid regression line that in the picture shows the estimated average weight. Right? So estimated average will be always on a line, but the actual average will be not exactly on the line. It will be a little bit above or below. It always passes through the point x bar y bar. Right? Both line SD line goes through x bar y bar point, and regression line also goes through x bar y bar point. So instead of rising 1 standard deviation in weight for every standard deviation in height, it rises only 0.4 times standard deviation in weights per SD in height. That is why most dots in the tall group lie below SD. Okay, so this is what Garrett saw earlier. So if you consider, for example, if you consider this stripe, those people are above average in height. Those people are above average. So put them balboth and minimum stripe the balboth. What can you see? And then make a minimum good edama very good in may good roda. Okay. You can look at the Pahalatan. Average is 73, meter 73, 73. So may pattern regress villa. So that is because actually R is equal to 0.4. Right? If R also equal to 0.9, it will be little bit above here. The amount that it is regressed is less in that case. Right? If R is smaller, it will be regressed by a large amount. So take the අනිත් පැත්තට මේ පැත්තේ අය අඩු වෙන ප්‍රමාණය මෙතන ඉඳලා එන්නේ. Right? So because this, if you consider any stripe here, they will be below average, right? Below average in the height. So their weights will be also certain amount below the average. So therefore we have to consider the decrease like that. It will be again R times SD of Y decrease in that size. Okay. So it's again mentioning the same thing. The regression line for Y on X estimates the average value for Y corresponding to each X. So it's an estimation actually. Associated with each increase of one SD in X, there is an increase of only R times SD of Y on average. So here the word increase, assuming that it is a positive. Otherwise, this will be R will be negative now, so it will be a negative increase. That means a decrease. So this picture shows what happens if you in the average point. If you increase your X value by 1 SD, then Y on average, not each Y value, Y on average. That means the average values of Y for this X will be R times standard deviation above the average of Y values. Right. So can we why this it says R times standard deviation of Y? Why it is not some other number times 10? Right. They are just mentioning it without any proof actually. Right. So proving it is a little bit mathematical, and they have not done in that way. But let us at least check whether this R is the factor, suitable factor here, at least considering few particular cases, right? So it has to be true for all situations, right? We will not be able to prove that the amount of increase or decrease is R times SD of Y mathematically if we don't do a little bit of rigorous mathematics. But they have given us the formula. We will just check whether R is suitable for that as a factor, at least in few situations. Right? So for example, if there is a no linear association, we know that R is equal to 0. So if there is a no linear association, when X is increased, Y is not increased. So therefore, the increase is Y in Y on average is 0 times SD of Y. So that will be 0. So that is meaningful, right? And if you consider R is equal to positive 1, that means all the line points have to be on the line on the SD line. So in that case, if you increase X by 1 unit, Y has to be increased by 1 SD. So R is equal to 1 in that case. That is correct. And similarly, R is equal to negative 1 is meaningful in this case. But for other general cases, we cannot prove it that the factor has to be R without mathematics. So it is not in this book. So therefore, I will not consider that. Right. So let's look at an example. Activity. Okay, let's call it activity. Shall we do this? Okay, because I don't ask you to do activities usually. So let's do it. Let's try to do it. So we have some 16 age 18 men. Average height of them is 69 inches. Their standard deviation is 3, and we are considering weight 190 pounds, and SD is equal to 42. R is equal to 0.41. So using what we just mentioned, estimate the average weight of men whose heights are these numbers separately. Let's do the first one. So if the average height of the people that we are considering is 69, it is the same as the average height of the old people. So we are not going any amount above or below, we are on the same point. So then in that case, average weight will be average of weight, same point, there will be no so average in that case 190. Okay, this one. 66 is one standard deviation below the average, right? This is one standard deviation. So this is 66 and this is 190, and we are now considering this 60. This is 69. We are considering 60. So this is one standard deviation of x. So what we are asking is, on average, what will be the weight of these people? So they will be, on average, r times SD of y below 190. So 190 minus r times SD of y. R is equal to 41 and SD of y is 42. So similarly, you can calculate these things also. You can see 24 inches, how many standard deviations above or below. It doesn't have to be a full number, 1, 2, 3, it can be 1.25, any number also. Right. So in that case, so in this case, r times 1 times standard deviation, because we are moving 1 time. If you are moving 2 times, then it will be r times 2 times this difference. But there is something that you have to be careful when you are predicting like that. 69 inches is the average actually. That is actually within the x values and the y values considered for this particular analysis. 6 is also in that range. But of course 24 inches means 2 feet. So there will be no men in this sample with 2 feet tall, right? So 2 feet will be far below here, which will not be contained in the sample. Therefore, we should not actually predict the weight of these people and these people. Well, 0 is actually practically not meaningful, but still one might try, even those are not meaningful. But in this case, they are not practically meaningful thing to do. So that is one important thing when you are predicting the y value or the average y value for a given x. That x value should be a value within the range of the data, right? In the data, because we don't know what happens actually. We are assuming that this is linear, at least in this region. After that, what happens we don't know. Maybe it's going like this, right? Or it's maybe coming down. We don't know. We don't have data. So therefore, we should not try to predict values beyond the range of the data. Okay, so this is again coming to more description about the regression line. Now they are actually going to talk about the regression line. So here they are considering the same data, height and weight, but what they have done is now for each separate value of height, for example, they have considered all the people in the sample with 61 inches. There were 2 people in the sample. So they have calculated their average weight. So when the height is 61, average weight was whatever this value here. And then with the dot there are numbers indicating how many people in the sample with that x. Right? For example, if you consider here, with this height, there were 54 people in the sample, and their average weight was like this. So what they have done is plotted the average weight versus x. So you can see that they are actually, when the height is increasing, average weight is increasing, they are around a straight line. So you can draw a line through the points, kind of a smooth curve or a line. In this case, line is suitable. So that is what actually we mean by the regression line. Regression line. The average, actual averages will not be exactly on a line, but the regression line is a line that approximates the averages. Now, in addition to that, what can you see here? For example, in the middle, in this range, the points, averages are more close to the line. Right? But towards the end, for example, here and here, the points are a little bit more far away from the line. Why does that happen? Right? If you look at the number of observations in the middle, there are a large number of observations of weights for different x. For example, 54 observations, 68, 59, 64, 40 and so on. But at the end there are only few numbers, 2 here, 2 points here and so on. So that is the reason actually when you calculate the average, the accuracy of average is going to be increased when you increase the sample size. With the smaller sample size, the deviation from the actual value is going to be little larger in the average when the sample size is small. So that's why there are kind of, you can consider this as kind of an error, right, from the predicted value and the actual value. Actual average is here, predicted value will be here. So this error is larger, but error is here small, and errors are going to be smaller when you have large number of observations. Errors are going to be larger when you have small. So that's the idea. So the graph of averages is the straight line. So you can see that if they are not exactly on the line, they are bumpy above and below. The regression line is the smooth version of the graph. In this case, it's a straight line. You can use a straight line. In the middle of the data, many observations exist, and the points averages are close to the line. By the ends, averages are a little bit away because there is a larger variability. So this is just a warning, right? So this is again. This again shows you should always look at the scatter diagram. Even that can be done only in the simple linear regression. Actually, if you have several x's, it's not easy to draw a graph. But if you have one x and one y, always you can draw a scatter diagram. From that, you can easily identify whether the association that exists, if there is any association, whether it's reasonable to assume it is linear or non-linear. So the main thing is that if you see that, for example, you can, when you have data, if you want, you can calculate the point of averages. If the point of averages are not along a straight line, then you should not look at the linear regression method, right? So in that case, you have to usually either use some other method, or sometimes people transform these variables. Y, instead of y, they may be looking at some other, like log y to the power y, y square, and x instead of x, they may be considering some other transformation. Then the relationship between might be straight line, then you probably able to consider the linear regression. But general idea is, if the association seems to be non-linear, then straight line model is not suitable to predict. So graph will show you whether a linear straight line model is suitable or not. Okay, so up to now we consider the averages, right? On average, right? Given a value of x, what is the value? What will be the value of y on average, right? So we use the regression method, right? That's what we call the regression method. To get the estimate the average. So if you say, for example, one standard deviation above the average of x, then your prediction will be average of y plus r times st of y. So that's what you call the regression method. But if you want to estimate, if you have one person, if you know his height, if you want to predict his weight, still we use the same value, average. Right? But of course, in that case, we know that his actual weight may be much more variable than the average, because with after the average there can be some other variation also. But anyway, there is nothing that we can do. If you want to predict the individual's y value, in this case weight, we still use the average value as the estimate of the actual y value. So here there is some idea that you have to understand. So suppose, for example, you are given only the weights. We are not given the heights. Right? And you are shown a person and you don't know the height of that person. You are asked to predict his weight. But you are given some summary statistics of weights. Right? For example, suppose you know the average weight of people. Right? You know the standard deviation of weight of people and so on. But you don't know anything about X height. Right? So without knowing X, if I ask you to predict the weight of a person, what is the best prediction?
The average.
Huh?
The average.
Average. That will be the best prediction, right? Of course, you will look at the person and then whether. But best thing, I mean, without considering like that, the best prediction will be the average. But if you know the values of heights also, then you can use the regression method. Right? You have more information, right? Then you can use the regression method, and usually that estimate will be more accurate on average than your estimate without using X. Okay. Okay, here this is again a simple example. A man is, so this is an individual we are talking about, not the average now here, predicting the individual's weight. A man is 73 inches tall, predict his weight. Right? So 73 is, if the average is 70, 73 is one standard deviation above the average. So therefore the expected weight will be the average weight plus R times 1 times 45. Right? 45 is the standard deviation of Y. Right? So therefore the predicted weight will be, if the average is 180, that will be 180 plus this number, that is 80, 190. So if, for example, if you consider all the people whose heights are 73 inches, then the average, the predicted average weight will also be the same number. If you just consider one person, still we cannot do more than that. We just predict it by the average at that case. 198. So this is another example. So the calculation is very similar, but the general rule is therefore, if you have additional information, of course you can use the regression method to get a better estimate. So the limitation you have to remember when you are predicting always, one thing is that the value of X has to be a value in the range of the data, and of course when there is a nonlinear relationship, this method cannot be used. Here we are assuming that this relationship is a straight line relationship. Okay, so we can estimate the average Y value for a given X. We can estimate the individual Y value for a given X using the same value, actually same method. In addition to that, for example, we can calculate or estimate the percentiles also, right? Percentile. If you remember what a percentile is, right? Suppose, for example, you have a normal distribution. On this axis, Suppose you have some value below which the area is, or the proportion or the percentage is, say, for example, 5%, then this value is the fifth percentile. Right. And similarly, so from here this will be 50%. So this mean will be the 50th percentile, which is the same as the median. In this case, if you have a normal distribution, which is the same as the second quartile. And like that, that's what you mean by the percentile. If you consider a value below which the area is 90%, then this value is called the 90th percentile. So in this example, as a student is at 90th percentile in one exam, SAT score, find this percentile in GPA. So we are given here the mean and the standard deviation of SAT scores as well as GPA. Right? So using those, we have to find out if a person is now not giving the value but giving the percentile. If a student is in the 90th percentile of SAT score, find his percentile in GPA. Right? So how do we find out that? We have to find out 90th percentile, how many standard deviations above the mean. Right? So once you find out that, then you can apply the same previous method. So the 90th percentile will be, right, so you have to find out what is the Z value. How many Z's from the zero value here, right? Or if you consider, because these have different means. So, for example, SAT value has average 550 and standard deviation 80. Right? So we are considering SAT here. So 550 and then we are assuming again approximately normal. Standard deviation is 80. So we are told that one person is at the 90th percentile. So we want to find out how many standard deviations above this value, right, percentile. Right? So you can do that, or you can convert directly into Z values and then take Z as giving the how many standard deviations. Because Z values directly gives you how many standard deviations above the mean or below the mean. Right? You do the same thing here. You assume that is x here, and then x minus 50 divided by that. That will be the right. So it is. But of course, 90th percentile you cannot find out directly using this one because you don't know the area under this one. So that's why you always use the standardized method. Right. So once you find out the Z value corresponding to the 90th percentile, right, you will see that Z is equal to 1.3. So if you are using that particular table, this area is 0.99, so this area is 0.1. But in the table you have this kind of area. So if this is 0.1, this is 0.1, this will be only 0.8. So when you are finding the percentile Z, you have to find out the Z value that has closest value to 0.8. There will be no probably exact 0.8 as the area. So in that case, you have to go for the closest Z value corresponding to 0.8 approximately. Right? So that will give you 1.3. Right? So that means this value is 1.3 standard deviations above. Right? In this one, this is the 90th percentile corresponding to Z in the Z distribution. That is the 90th percentile. So that is 1.3%, 1.3 standard deviations above the SAT value. Therefore, in the GPA, GPA of this particular student has to be average GPA plus 0.14 times 1.3, R times how many standard deviations above. Or if you just consider how many standard deviations above only, right, if you want to get the actual mark, that's how you do average plus R times how many standard deviations above. But this gives you how many standard deviations above, 0.4 times 1.3 standard deviations above the average. So therefore that is enough for us to calculate the percentile in this case. In order to calculate the percentile, now we have to know what is the This value is approximately 0.5, right? So what is the percentile when Z is equal to 0.5? That's what you have to find. 0.5 or 0.52 approximately. So that again can be found using the table. Now the area, earlier you found out the percentile, and now you have to find out the area to find out the percentile. Earlier the percentile was known, you have to find out Z value. Now the Z value is known, you have to find out the percentile, that is the area below. Of course, what is given in the table is this area, 0.5 and negative 0.5. You can find out this area from the table, and therefore you can find out this. Right. So those things can be done, simple calculations. So these are some examples we can go through that in this game. So when you look at actually, if you there are two examples in the book. In this one, we are looking at when a person is at the 90th percentile of SAT, his percentile for GPA will be little less, right? 69 percentile. And this is another example when the person is in the lower, right? We are considering above average case and below average case. 90th percentile is going to be above average case. Now we are considering a below average case, because again they are going to explain here that regression effect that earlier we discussed. If you consider a person whose SAT score is below average, for example 10th percentile, his GPA percentile will be a little bit above, more than 10. Right. So when you calculate the percentile of the GPA, we find out that it is 31st percentile. Right. So it has increased. Right. GPA for the SAT he was 10 percentile. Right. When you look at the GPA, it's increased. So that's what we looked at earlier also. Right. Those who are below average in one variable, for the other variable they can be larger on average, and therefore the percentile will be larger. And similarly, those who are above average for the first variable, second variable, the average will be little less than the average. So therefore, percentile will go down. So that's actually naturally happening always. That is what you call the regression effect. So that's what is explained here. Right. Using those two examples, also they are explaining that the same thing. So that's what we call the regression effect. That's what this originally what Galton called regression towards mediocrity. So if R is equal to 1, absolute value is equal to 1, that is if R is a positive 1 or negative 1, there will be no regression effect. But otherwise, always there is some regression effect. Actually, I tried to produce another picture to show you further about this regression effect last night. So let me see if I can find that out. Just to show you this is happening always, not only for these two particular examples, height and weight and so on. So what I did was I generated some data, right, to see whether this happens always. Right. So I generated some data, and this is my scatter diagram in that case. This is the this is SD line actually. So the points must be on this line if R was 1, but in this case R is not equal to 1. So I also calculated the average values in different stripes. In this case, what I did was I didn't consider equal weights, but I considered different stripes here, a large stripe, this is a small stripe, so that the number of observations will be roughly the same within each stripe, right? So here the number of observations within this stripe is the same as number of observations within this stripe, and so on. So these are the averages, right? Or if you consider the y variable for all these x values, this is the average, and it's going to be in the middle of that. And similarly, if I consider this particular one, roughly the same number of observations in this stripe, average is here, so I have plotted it versus the middle value, right? So you can see that again the same thing that we did so earlier. The points are close to a straight line. We can draw a straight line through the points. Actually, this is not the, sorry, I made a mistake. This is not the ST line, this is the regression line. Right. So the points, the regression line goes through the points, but again you can see that in the middle, the points, average points are more closer to the regression line, whereas here and here, even if the sample size in this case is the same, the deviation is large here. So what I wanted to show here was the regression effect. So this is the, I'm considering here, for example, test reads. Suppose the same people are taking, this can be done for any example, but I'm just considering a situation where there's a group of students who are taking one test, and the same people assuming that they are taking this another test. So I'm considering the relationship between test 2 marks and test 1 marks is actually generated data. So suppose according to my generated data, the average marks of test 1 was somewhere here. Right? And what here is, this is about the test 1 marks, these are the test 2 marks. So these are this height shows you the average test marks of the test 1 of those who are below average. Below average. So make it larger. Oh, sorry.
Yeah, the plus sign there.
Okay. So for the test 1 marks, if I look at the two groups, below average people and above average people, below average people had the average this number 56.3, above average people had this average 83. For the same people, these are just generated data without doing anything, but this happens always. You can see that the average of these people, below average people, now has increased, regressed towards the average, gone up. Average of these people gone down in the second test, regressed towards the average. So this happens always. So that's what you call the regression effect. Maybe we can explain this like this. For example, these people, some of these people will be close to average, but some people will be far away from the average, because these are just below average. When you consider below average, so for example, below average means all these people, above average means all these people. But now mainly this effect happens because of these people and these people. There are some, maybe somewhat small number of people whose x value is, at the beginning, x value is very small and also very large, very large. These very small values and very large values usually occur because of large random errors, large what you call chance errors. So for those who have large chance errors in one situation, for example in a one test, are not going to have the same size of chance errors next time also, right? Because these are chance errors, right? Usually their chance errors in the second time can be quite smaller, because they are going to be, most of the values are always going to be close to the average. So try to be close to the average. So therefore these values are going to be, for the second test, their averages are, their errors are not going to be as large as that. The errors will be small, most of them, but not all. Similarly for this one also. So that is the reason to happen this kind of thing, right? Those who had large errors in this situation tend to have small errors in the second situation. So therefore on average, their average will be now going up. So this is not explained like that in the book, but I try to understand the situation, and this is how you explain it. But what you have to remember is this is always happening most of the times. This phenomenon is existing in usual regression, simple linear regression situation. So that's what Galton noticed in his experiments also. So that's what he called regression, regress to the mediocrity or regression to the average. Right. But some people try to attribute this phenomenon to some effect of something. Right? Some people say that this is happening because of effect of some maybe variable, effect of some phenomenon and so on. And that is what called the regression fallacy. Regression fallacy. Right? Because we have to understand this is not because of any particular reason, any external reason. That is a natural thing that is happening always. So if you try, you should not try to attribute this behavior to some other external factor. Right? You should understand this is happening always, and that's called the regression effect. Right. So shall we take a small break? It's 10 o'clock now, and then we continue from there.